of the two sections on the homework. So 2 sections doesn't sound a lot, but I think from experience we know when it's not a lot of sections there can be a lot of work in them. Of the 2 sections you're going to do, this one is by far the easiest. It's quite theoretical in the sense that it's just pure math, and it's a process on dealing with line integrals, in particular very special kinds of line integrals. That is line integrals that have a vector function that's a conservative field. So let's get the theory. First thing we're going to look at is, how do you tell if a vector function, also called a vector field, is a conservative field? Because there's lots of different kinds of vector functions in the world, but there are a relatively small subgroup of them that have a lot of structure to them. And these particular ones are called conservative fields. And I was looking into it just because I guess I was bored. And it's actually used by people, so it's not totally theoretical. The story that I was reading was to do with potential and, oh God, what was the other energy? Something like potential and kinetic energy of a moving object. And essentially, if you're moving through like a vector field, which could be a wind field, it could be a magnetic field, whatever it is, that the sum of the two things always equals the same number. And evidently that is a provable thing by using what's called the fundamental theorem of line integrals. So back to our job. How do you tell if you have a vector function that it's a conservative field? So imagine you've got a vector field, that guy. A lot of the time we just call the guy F, but it does have X and Y in it, right? And let's suppose that this vector function is made up of these two components. So I'm actually going to use P of xy to be, you know, the x squared y plus y cubed that goes here, and the x minus y squared that goes there. Because when you remember these things, isn't this two separate functions? This is the x component and this is the y component. Well, here, this is basically a pure definition. The vector function f is a conservative field if that's true. So if the derivative of the first thing with respect to x is the same answer as the derivative of the second part, right? First part with y, second part with x, getting back to front. If they're equal, is a conservative field. So let me show you some just examples of, I think the early questions do that. They just give you a vector function and they ask you to prove if it's a conservative field or not. So here's my first example. Oops, Kavika's just turned up. So f is going to be xy plus y squared, and q is going to be x to the 5 plus 2xy. Nothing particularly unusual about that. This is going to be p, this is going to be q. So I'll find the partial derivative of the first guy with respect to y. And if you differentiate partial derivative of this thing with respect to y, you get an x plus 2y. And if you do the second one and you do a partial derivative of this fellow, which we're calling q, with respect to x, You get that. Now, it's not hard to check that these are not equal. So this particular vector function is not a conservative field. So I'll just say CF, so I don't have to keep saying conservative field. So as the question goes, it's a bit like magic. This is what you do to find out if a vector function is a conservative field. You just find the first component's derivative with respect to y, and the second component's q's derivative with respect to x. If they're the same thing, you get a conservative field. Now, if you randomly pick functions that go here and randomly pick other functions that go here, can you see that it's probably going to be more likely than not that you get an example like this? It's not going to be a conservative field, right? There has to be quite a lot of structure in the P and the Q to make this relationship work, right? So it's not a kind of everyday thing, but they are so cool when you get one that works. If you can find one that works, they are so useful that it's worth it just to find that limited number that it works on. So that was an example of it not working. I hope this is an example of one that does work. So here's our vector function. I think the textbook likes to call it the first guy I plus the second guy j, which is fine. I just don't like that notation because I make too many mistakes with it. So we have this fella plus sine y. We have this fella plus x cosine y. And we're going to see whether or not this fella is a conservative field. That's the P, that's the Q. The partial derivative of P with respect to y. Well, if you differentiate this with respect to y, you get e to the x. Differentiate this, you get cosine of y. If you now do the second guy, but partial derivative with respect to x, this guy gets you e to the x, and this guy gets you cosine y. And you see, like magic, they are equal. And because they are equal, this vector field is a conservative field. Then F is a conservative field. Now, as a process goes, it's not that complicated, right? And as long as you know how to find partial derivatives and you remember, which I almost forgot, that do the first one with y and the second one with x. If you get the same answer, great, conservative field. If they are not the same answer, you don't, right? It's not a conservative field. Any questions, or so far so good? We're good, okay. Well, that was step one, to remind you who step one was. How do you tell if a vector function is a conservative field? That's how you tell, right? You do the little test. Let's move on to two then. The fundamental theorem of line integrals. And it doesn't even make a good word. Do you know how, like, Soccatoa, at least you've got a chance to say it. If you try and say that out loud, it's like Fatoli or something. It sounds Italian to me, but it's not very interesting, right? The fundamental theorem of line integral, what does it say? It says if you have a conservative field right, so that's a conservative function, right? This guy. Then the integral of C right, over some curve, so it's a line integral of f dot dr. We've done enough of those in our life. Remember the usual line integral where you had to spend a lot of time converting everything into x's and doing a whole load of stuff? Well, that guy there, it is equal to this guy. There's still some more detail to be added to this. C is your curve or your line, and it's going to be described by a parametric curve RT, and it's going to be from values of t to from A to B. The little function f that they have here, so that's a different guy from this. This little function f has a name. It's called the potential function. And it is the potential function is a special function that has the property that, remember doing the gradient function? The gradient is equal to your f. So what does this allow me to do? It allows me to find a line integral by basically just finding the value of the potential function at the end of the journey and subtract the value of the potential function at the end of the journey. And it doesn't really care what r of t is, which is amazing. So what does that look like? Well, can you imagine that you have a vector field? Right, it's got all these vectors doing their thing. Right. And you've got a guy that starts here and he finishes here. So this is what happens when t equals a, and this is where it is when t equals b. Now that's your line integral, your c. And what it's saying is that it doesn't care what the function is, it just needs to know where you are when you start and where you are when you finish. So what's the x and y coordinate of the beginning of the curve? What is the x and y coordinate of the end of the curve? So that's what that's saying. And you just evaluate the potential function at those two places, and the difference between them is the answer to your line integral. It's even more interesting than that. Can you imagine a totally different curve that starts and finishes at the same place, like that dotted one? Call that C2. Do you know that that line integral has the same answer as this line integral? They are totally independent of the path, which is an amazing property. You would think if you go through a vector field and you decide to weigh, zoom around and do all sorts of weird stuff, that you would expect that different pathways would end up with a different line integral, right? I traveled further with one, so it should be bigger, or some idea like that. But the theory is, and the math says, no. It only really cares of where you are to where you finish, and the difference between them is going to be the answer to your line integral. Analogy, I'm not very good at physics. Can you imagine you've got an object and it's 20 feet above the ground? That object has got a certain amount of potential energy, hasn't it? Right. Now, if I take that object and I move it up and I move it down and I move it sideways and I move it back and then I move it somewhere else, but I only find out that when it's finished, instead of being 20 feet, it's now 40 feet above the ground. Isn't the only difference in potential energy the first answer take away the second answer?
Pretty much.
It doesn't really matter how you got to the top of the hill or the bottom of the hill, wherever it is you're traveling. It just matters that you get there. And so the pathways are irrelevant, which means that when you do these types of line integrals, You do not need to do what you had to do in the past. What you had to do in the past is you had to take f. That would be x cubed y plus yz squared, right? And you turn them all into parametrics, all in terms of t. Wouldn't the dr become r dashed t dt? And so you ended up with a big ugly integral, still a single integral right enough, but a much uglier integral dt. And some of those integrals could be atrociously difficult to do. Can you imagine we didn't give you easy ones? Believe it or not, we gave you easy ones. Can you imagine we gave you a function where the x guy ended up being, you know, e to the t sine t cubed, and the other one ended up being, you know, square root of t over log t? You do not want to integrate functions with those kind of bits to it.
Oh, no. No, that's a bad idea.
But if it's a conservative field, you don't need to. All you need to know is what's the answer at the start and what's the answer at the end, and you're done. The hard part, because there has to be a hard part, is you have to find this function f, the potential function. Right? But once you've got that, boom, it's like grab a calculator and you're good to go. So I guess it's time to show you one, right? Because we're just talking in general terms here. So here we can go. Here's my vector function. So y squared take away 8x, and it's a 2xy. And I would like to do okay, this is going to be my parametric equation of the curve, right? So who shall I pick? Kavika, give me the x component of the curve. So give me something here in terms of t.
In terms of t?
Yeah.
3t squared plus 2t.
Okay. And I'm going to put in an ugly one there, right? So imagine this curve, right? And we're going to do t equals 0 to 1. So you're going to pass through this vector field with this curve from 0 to 1. So I'm making no attempt to pretend that I know what this curve looks like. But can you imagine this is our vector field? And the guy that we've just done looks like that, right? And has an orientation. It's going that way. Our question is going to be to find the standard line integral. Now, let's see if we can get a bit more autofocus in here. Come on, you can do it. Okay, so imagine how you would do that the last time that we did these.
Oof.
Right, firstly, when we have to find r dashed of t, not bad, but it's doable. Wouldn't all these y's squares be turned into this guy? Wouldn't all the x's be turned into this guy? Wouldn't you do a dot product with this guy and the derivative of that guy with a dt at the end? And then you just have 0 to 1, you know, as your start and finish value. I could imagine that that would be a really, really horrible integral to do. I'm not even sure.
Yes.
Yeah, if it ain't even possible, because sometimes you can't integrate things. You know that there are certain functions are non-integral by the techniques that we know, right? Don't want to do it, so let's not. let's use the fundamental theorem of line integrals. I'm going to do a couple of cheats here for speed. Can you trust me that I've already done the check and it's a conservative field?
In my head, yep.
Right, we're good to go with that. So, I need to find the little f, right, the potential function. And all I know about it is that its gradient is that. Now, isn't the gradient the partial derivative with x and the partial derivative with y? Right, remember that's what the gradient function is. The first component is the partial derivative of f with respect to x. The second component, the partial, I'm going to make these little baby ifs. So I know that this fella has to be equal to that. And I know that this fella has to be equal to that. So all I need to do right now is figure out what unique function, because it's always going to be one answer and only one answer, is going to work. Well, do you know we kind of work backwards? By that I mean, if I know what the partial derivative of something is, shouldn't I be able to figure out what the original function is? By integrating, essentially. So, if you integrate this fella with respect to x, shouldn't that be what f is? Agreed? Well, let's integrate it. If you integrate y squared with respect to x, don't you get y squared x? It's like 5 gets you 5x. If you integrate negative 8x, don't you get negative 4x squared? So far, so good. I'm going to make this guy go away.
I'm following, yeah.
Oh, wait a minute. Plus a constant.
It's been a long time since we used those.
Yes, but when you do integration in this world, the constant is actually some function of the other variable. You know, wouldn't y cubed be a constant in terms of x? Because what happens when you differentiate y cubed? It disappears on you, right? So I'm going to have to call this g of y. So it's a placeholder. If I do the second fill-in now, which is 2xy, if I integrate it, I get dy. Now, what do you get if you integrate 2xy with respect to y? Well, you add 1 to the power and you divide by the new power, but isn't the x still there?
Xy squared?
And you get xy squared plus a constant. Now, won't the constant in this case be some unknown function of x? So let's call it h of x. So what we have here are two connected pieces of information, and they are telling us who this potential function is. So what we have to do is merge them together in such a way that you get a single function of f that has all the features. So here goes. Would you agree that both of the terms contain an xy squared? So that's a good. What about the negative 4x squared? Well, this guy has a negative 4x squared. This guy doesn't have an explicit version of that, but couldn't hx be a placeholder for it? So that means you get this. Now, you all want to see the shortcut way of doing that, don't you? Watch this. There's your answer. If it ain't an arbitrary thing, right, you can cover it up. Now, when you see what's left, you don't put them together in an add kind of way. You don't say that and have two of them. You just say, I've got one of them and I need the other guy. So there's the two bits. which means that we now have this mysterious potential function. And you've got to compare the work we've just had to do to what we would have had to have done in the old world, right? Remember that horrible integration by parts and big equation this big and, 2 days later, that kind of question. So, continuing with our puzzle, just to remind you that the curve RT was 3t squared plus 2t, and then e to the t sine t, and that it started at 0 and it finished at 1. And according to the theory, the line integral over c of this fella is just the value of the function at essentially the end, take away the value of the function at the start. Now they call it R of B, R of A. And if you think that's A and that's B. So let's see what that looks like. At the beginning, isn't the curve at position R0? Now, according to this, R0 is so many nothings plus so many nothings, e to the nothing times nothing. Oh, it's basically, it starts off at the origin. And what about R of 1 then? 3 lots of 1 plus 2 lots of 1 gets me 5. 1 times sine 1 is, I'll just call it sine 1. That means that's the coordinate of where that shape started, and this is the coordinates of where it finished. Right? So the line integral is the value of the function at this fella, take away the value of the function at that fella. So it's the potential function at the end of the curve, take away the potential function's value at the start. And that's just a matter of taking our xy squared minus 4x guy and seeing what we get. Right, if we plug this fella in, you get 5 times the sine of 1 squared. That was my fault for picking a messy one. Multiplied by 4 times 5 squared. Oh, do you know 0, 0 is just 0? Right, if you plug 0 into here and here, you get 0. So that one's easy. Well, that's the answer. It's not particularly pretty. It's 5 lots of sine of 1 squared, take away 20.
Isn't it minus 100?
Is it minus 100? It would be, but I plugged out 5 as a common factor that has the same effect.
Fair enough.
But I mean, I should put that in because you're never quite sure what the book's going to think of as, right, it's that guy, right? Same thing. So we got a little process here. If you can remember the steps in this process, you can basically integrate any line integral. You can find any line integral as long as it's a conservative function. Now, the one that I just did there was totally random. Apart from the original function was conservative. I had to make sure that's true.
That certainly makes things a heck of a lot easier.
It is. I wish the restriction on a conservative field was less restrictive, because it's quite hard for a function to be conservative, right? When it is, they are really cool. But I think they may appear in real life more than they appear in math. There's a kind of symmetry or balance to conservative fields, which I think in many situations is realistic. I'm trying to find one here.
Would it apply to like magnetic fields?
Yes, it applies to magnetic fields, any kind of force field, any kind of wind, currents, I mean, if you can model it with a function at least, you can do it. Right. What I'm going to do right now, because I can't think of, off the top of my head, I can't think of a conservative field. They're kind of hard to just pull out of the air, is I'm going to nip in and pick one of the books. Right, so right now, I hope you are looking at the WebAssign homework for this section. Nod your head or something. You're not? Yeah? Okay. Right, so I'm just going to scroll down. Oh, before we do, in question 4, here is your vector field. It's 2xy comma x squared. If you do a test on that, it is conservative. And then here are 3 curves. They start here and it kind of zigzags like a sine curve. It starts here and it goes a big arc. And it starts here and it goes a lower arc. And it says, explain why this has the same value. If you're a conservative field, isn't it totally independent of how you get from here, which is the start, to here's the finish? The line integral will always be the same answer in a conservative field. Right. So that's what that was about. And then they ask you to evaluate it, but you can do that. That's too easy. Got to stop somewhere. Okay. I have a 50-50 chance that I have picked a conservative field. If it is, then you keep going. And I think the way this question is phrased, we're good to go, right? So that's fine. If it wasn't, I would just say does not exist, and that's the end of the question. So I guess you might get an easy homework question where it's not a conservative field, in which case you just stop there when you find that out. Okay, so
yeah, it's conservative.
Checked in your head? Okay, so I'm going to assume that it's already been checked and that it worked, and so it's conservative. Although just looking at it, it's very symmetric, isn't it? In a kind of pseudo-symmetric way, right? So that's a good chance it would be anyway. Now, we need to find this guy, the potential function. So here we go. Basically, that, right? This guy is the partial derivative of f with respect to x, and this is the other one with y. So if we integrate x squared y cubed with respect to x, then we get, add 1 to the power, we get 1/3 x cubed y cubed plus some function of the other variable. We'll call it g of y again, right? So if you integrate this with respect to x, you get that, plus a constant in terms of y. If you take the second guy and you integrate him, you will get, oh, now remember my little trick. You can't see any of this. I just realized that. There, give you a few seconds. So here is my function, that guy. We've already assumed that it is conservative. We checked that and it works. If you take this fella, he's going to be the partial derivative with respect to x. So if you integrate the first component, that would be a candidate for f. You get 1/3 x cubed y cubed plus a constant. And all you do is remember that the constant is a function in terms of the missing variable, in this case y. And then you do the same to the other one. And then you cover the two guys up. Do you see in this case, we're good to go. Don't they both share the same term? And because it's the same term then, our potential function, which is the name we give to this guy, is that. Now, I believe this particular function had a curve associated with it, but I don't know what it is, so I'm going to make my own version. Let's suppose it was t squared plus t and t cubed minus 1, just for argument's sake, right? That was the curve they wanted. And it's going to be from 0 to 1. Right, so that defines what the curve is. Right, now we're good to go. If you find the line integral over C, so this is your curve, you find the line interval over the curve of f dr, it will be the potential function at 0. Potential function, let's start again. The potential function at the end, take away the potential function at the beginning. Okay, I guess I should find out where these functions happen to be. Right, according to the definition up here of the curve, when t equals 0, doesn't this end up being the point 0, -1?
Yep.
And when you plug in 1, doesn't this become 2, 0?
Mm-hmm.
So we're trying to find the value of the function, the potential function at 2, 0, take away the value of the potential function at 0, -1.
Is that just 0?
It is. What a cool question. Now, I haven't even looked at that curve, but it might be quite interesting if I get time, which I don't, to have a look at it. Because if I'm doing my analogy about 40 feet above the ground, can you imagine you're 40 feet above the ground and you finish up still at 40 feet above the ground? Wouldn't the difference between them be 0? Right. So potential functions could be positive or negative, right? You could end up lower than you started. You could end up higher than you started, right? So all three numerical values. That was kind of cool, 0. We could? Any questions? Do you get? I've only done a couple of these, but I think if you see enough of them, do you get? There's a kind of theme to them. There's a kind of way you do them. You check that it is conservative just in case. Probably will be. You then do the integrate with x and integrate with y. That'll allow you to find the little f, the potential function. You then just find out where the curve is at the start and the finish. And then you do the value of the potential function at the finish, subtract the value of the potential function at the end, and the difference between those two numbers is what the value of your line integral would be equal to.
We did actually a little bit of that middle part earlier this quarter.
We did, didn't I? think we did a question where we never said that's why you were wanting to do it, but didn't we do a question where you knew what the gradient function was and you tried to figure out what the little f that you would need to start with? Yeah. Didn't we do one like that? They never said why, but now I guess you know why. I was just getting you like warmed up for something you're going to do a lot of now, because this process.
I thought that little bit looked familiar because I remember I'm going to go over that myself because I missed the class meeting on it.
Right. We good? Right. Let's show you a little theory. Suppose I have a conservative function and I want to do the line integral and C, and I'll draw you a picture of C. You start there and you went all the way around the curve and you ended up at the same place that you started. That's called a simply connected region. Basically, it's a loop. I know the answer to that without being told anything about F or the equation that makes that curve C happen. Because you start and finish at the same point, what's the answer to that integral, that line integral, guaranteed to be?
I'll let somebody else field this one.
Go for it. I heard it. Who said it? Somebody else said it.
0.
0. kind of cool, isn't it? I hope you get one of those questions, because if you notice it's conservative and you have a little quick look at what the function looks like, you all know how to do parametric curves in your calculator so you can actually see what it looks like. Most of the time it's a kind of starts here, zigzags, and then finishes up here, right? It doesn't do anything particularly interesting. But occasionally, just occasionally, don't you get a circle? Or an ellipse maybe? And if that happened, you could short circuit the whole process, couldn't you? Just say, hey, 0, next question. Or you could fight your way through the math and get 0. Are we good? So yeah, I think we get time for another one of these. Basically, the entire section is that question. Find the line integral. Now, occasionally they put a story behind it and they say, find the work done. And to get the work done, it's a line integral f dot dr. So as long as you tell me who f is, right, and as long as you tell me the parametric equation of the curve, you're good to go. Right. But for this next one, let's go 3-dimensional. So that means we're going to take what we know and try and take it to the next level. So, oh, there's a good one. Question 7. I'll write that down. So our vector function is in 3D. It's yz, then it's an xz, and I think the other, oh, I'm wrong. I thought I knew what the last term was going to be based on symmetry, but it isn't. It's xy plus 6z.
Okay, so how does the derivatives go on this one for
for a 3-dimensional, right? There is a test for it. It's a big long thing, but it basically you have to show that the 3 pairs of partial derivatives are all equal to each other. So you say that the first one with y is the same as the second one with x, and the second one with z is the same as the first one with y, and then you say the first one with z is the same as the third one with x. So can you imagine if you took x and y, you just switch places for who you do the derivative of, right? So you've got x, y, and z components. I do not want to get caught up in that. Can I tell you, I know it's a conservative field.
Okay.
But you can look it up and find out what it is. So that means the partial derivative with respect to x is this guy. The partial derivative with respect to y is that guy. And the partial derivative of z is this guy. And when we're finished, we will have this fella. And then I'll go back and look at the question and find out start and finish values. Right, so here goes. If I want to get f, you integrate yz with respect to x. Now don't get too caught up in the weeds here. This is not a hard integral to do, because aren't y and z treated as constants? So won't you just get yzx, which I think is nicer to call xyz, right? Yzx. Now, what is the constant? The constant is anything that doesn't have an x in it. So technically, couldn't the constant be a function of y and z? So we'll call it g of yz. That's really just a placeholder, right? That's just a place where we can use it to fill in some stuff if we need an extra term from somewhere. Now let's try the second guy. Oh, wouldn't you just integrate that and xyz plus a constant? And this time the constant is anything that doesn't have a y in it. So let's call that h of xz, right? Just a placeholder again. Now the third one is the integral of xy plus 6z dz. Now if you integrate that with respect to z, you get xyz plus z squared plus a constant. And isn't the constant anything that doesn't have a z in it? So I'm running short of letters of the alphabet, k, x, y. Now, we have to put these three together. Now, if you cover up the placeholders, do you see that they all have an x, y, z in it? Is there anything else that I need to add for this thing to work? They all have an x, y, z, but
The 3z squared?
is there a 3 there? Well caught. 3z squared. So when I say these are placeholders, do you see they're just ways of making sure that algebraically we're covering our butts here? Because if you think about where does that 3z squared belong? Well, he belongs here. Good. Couldn't that guy be 3z squared? He's a placeholder for him. And couldn't this guy be 3z squared? Everything is consistent. Now, in this question, this three-dimensional one, they didn't tell you the curve. They didn't say r of t and give you, t squared plus 4t and all that stuff, although they could have. I think they went and said, you started at nothing 1, 2, and you finished at 5, 6, 0, right? That's not the numbers, but they gave you a location to start and a location to finish, which is actually all you need to know, isn't it? For the fundamental theorem of line integral, you just need to know where do you start and where do you finish. So the line integral of f dr is our potential function at that point, take away our potential function at that point. Now, here is the guy I'm going to use. 5 times 6 times nothing. Oh.
It's minus 12, by the way.
Which one is minus 12?
Oh, just the answer.
Oh, okay. So, where was I? 45, nothing, none. That's nothing. Take away. That's nothing. 3 times 4. Now, we've just managed to do an entire three-dimensional line integral. I don't think it's that hard compared to how you would have to have done it the parametric way, right? The previous sections ways. So have I fun. It might not have been difficult to do it the other way. It just would have been big, right? And messy and, time consuming. But this is kind of elegant, isn't it? If you're a conservative field, you just need to know who the potential function is, the little f. Evaluate it at the end, take away, evaluate it at the start, and whatever that number is, that's what your line integral would be.
I will say I do like it when there's zeros at one or the other of the points.
I think a lot of you probably get that a lot, because in a lot of the questions, I only skimmed over the homework, but in a lot of the questions, it's t equals 0 to t equals 1. So you can imagine that the numbers you're going to get in your coordinates will have a fair number of zeros in your answer, which is always helpful, just for calculations. And actually, t equals 1 is not bad either, right? Because you plug 1 into most things, it comes out without too much trouble.
Like squares and square roots, if it's a 1, it's just a 1. Doesn't matter how many of them you have.
Correct. Not much I can say about that. Yes, you're correct. Let's see. Yeah, we've got one last question, I think. Let's try and use our time wisely. Okay, so I'm back at the screen here. So I'll talk through some of these questions. Here's another two-dimensional one. You should check to see that it is conservative. If it is, can you see you now know where to start and finish? Right, you're just going to plug in the potential function at 2, 2, take away the potential function at 1, 0. Now, and a different story, can you see this three-dimensional one here? Now, I'm assuming the way they've phrased it is that the thing is conservative field. So you can assume that that's the case, then it saves you a bit of work. And there's the classic 0 to 1. Can you imagine taking this guy and doing the same kind of process we did a minute ago? If you plug 0 in here, you get 0, 0, 0, oh, the origin. And if you plug in 1, you get 8, 1, 1. So you can imagine it's from 0, 0, 0 to 8, 1, 1. So the minute you know the potential function, you're done. I'm just scanning through these guys. There's quite a few three-dimensional ones.
Ooh, cosines and sines.
Well, I was going to do one. I was thinking the log one looks more interesting. Let's do a log one, right?
All right.
Last one today. I'll write everything down this time. Oh, don't want it. It's asking us to prove that it is not conservative, which means you go and you do that big long test, and I don't want to do that one. I'm guessing that it's probably a not, just by the way it's phrasing. I want to do one that is. Right. Oh, darn it, we have to determine it as a 3D one. No, it's a 2D one. I want a 3D one. I'm running short of space here. Okay, the last one, 18. Evidently, it must be the worst of the lot. It's the last question. What do we get here? We get a y squared z plus 2xz squared. Check. We get 2xy z. And then we finish with an xy squared and a 2x squared z. And the curve is a parametric curve. And the x component is a square root of t. The y component is t plus 4. And the z component is t squared. And we're doing it from 0 to 1. Tell you what, let's find out who the start and finish guy is, since it's here. 0, 4, 0. You all happy where I got those numbers? I just plugged t equals 0.
Mm-hmm.
Finish. Right, we got them. Here we go then. Partial derivative with respect to x is this guy. The partial derivative with respect to y is this guy. And the partial derivative with respect to z is that guy. So this one we will integrate with respect to x. And of course, I've been doing a whole load of stuff. I'll give you a second to catch up with me here. So there's the original function at the top. Here is the curve in parametric form. I just found out where it is when t is 0 and where it would be at the end when t is 1, so that's where they came from. Here is my first derivative with respect to x. Here's my other one with respect to y, and here's my third one with respect to z. And we're just about to integrate this fella. With respect to x, you get x, y squared, z, plus some function that doesn't have an x in it. And then you have 2x z squared dy.
Hold on a second.
Yes.
Shouldn't the f of y be 2xyz?
f of y. Is there a missing here? Whoa.
I think you went a bit fast.
I went too fast for my own good. Did I write it down wrong?
Yep.
That is, yeah. Let me go back in. Sorry about that. I have y squared z, check. 2x z squared. So there isn't a y there. 2xyz, check. xy squared, 2x squared, z. Okay. So there isn't a y here at all.
No, there is a y there. It's the f of x is
Oh, it's this
z
fella.
plus 2x z squared. Might want to just start that over.
I can recover, even if you unfortunately can't. The first one, I think I started there and then thought that was the next term. That looks like my mistake. So there is a 2x, but a z squared here. That one is much cleaner. And I hope that I didn't screw up on this one.
Yeah.
Okay, so to find f, we're going to integrate this. I'm going to skip the line and just do it. If you integrate this with respect to x, you get x squared y z. And this guy here, integrate with respect to x, you get this fella, plus some function that doesn't use x. And that's your constant. If we integrate the second one, that's this guy, but with respect to y, we get, oh, x squared yz, plus a constant that doesn't have a y in it. And if we do the third one, and we do it with respect to z, we get x squared, x, y squared z. You do this guy with respect to z, and you get an extra x squared z squared, plus some function that doesn't have a z in it. So here are three candidates, 1, 2, 3. When you merge the information that they contain, are we all happy that they all contain an x, y squared z?
Looks good.
What else do they all contain? Or at least two of them do.
X squared, z squared.
And isn't this guy a placeholder for that guy? So if I just covered, that was, when I do my shortcut, if I just cover that up, don't you just merge all the details together into a single function that at least all the bits are contained at least once? Now, from this function's perspective, all I need to do then to find this line integral is to evaluate at the destination, take away the start. So what do we get? We get, well, we get a lot here. We get 1 times 25 times 1, so you get 25. And you get 1 times 1 is 1, so you get 26. And then in this one, you get nothing out of that. And you get nothing out of that. So 26. Apart from my usual, when I go fast, I screw up. We're good, right? Theoretically.
Math checks out.
Yeah, theoretically, there is no limit to how many dimensions your vector field can have. We've done 2 and we've done 3, right? As long as it's a conservative field. So can you imagine you had 4 dimensions, you just do the first one x, second one y, third one z, fourth one w, right? Integrate them all. merge them together. Boom, you got your thing. Proving it's a conservative field would probably be quite messy. So we'll assume that you're told it's one.
Sure, there's a theorem for it.
There is. I was going to say I'm pretty sure there's a matrix involved in it, but I can't remember for sure. But yes, there'd be a theory for it. You're never going to see a 4. I just thought it'd be fun to talk about that. Because when you start talking fourth dimensions, do you know that you lose all reality? You know, physical reality that our brains can cope with. I can imagine a vector field in 3D, right? If you walk outside and there's wind blowing all over the place, can you imagine that could be modeled by a vector field? Right, at any given point, the wind's blowing in a particular direction, right? That's what a vector field is. It tells you the vector at any given point, X, Y, Z, right? How the air is moving, right? And then you could imagine some object flying through the air in a curve. And that means you could find a line integral. But if you go fourth dimension,
we ain't got time for that.
We ain't got a brain. Your brain will fry. But if you're into it, if you're into theoretical physics, 11 dimensions, if you want to do string theory. So some of you, but mostly not most of you, will do that. Okay, that was a nice day today. We had a little hiccup at the start, but we finished. Any questions for good to business? Otherwise, we're going. Right. Now, I hope you got good out of this, because tomorrow your brain's going to hurt. I'm telling you right out the bat. Tomorrow your brain is going to hurt, because we're going to do a guy called Green's theorem. And that fella was a genius, because what he came up with was totally amazing. But you will find out what that is tomorrow. Bye-bye, everyone.
We'll see you tomorrow.
Thanks.
You're welcome. Bye-bye.